So we previously talked about deep sea sediments and both how they form and what we know about the distribution and types of sediments. Today we're going to talk some about shelf sediments. So this is a stratigraph of the of shelf sediments. You can see this dark line here is the ocean plate, and this light color up above is the ocean, and in between are the sediments. And so these lines are essentially formed by bouncing sound waves off the material. We'll talk a little bit more about that later, but you can see these layers that go through the ocean sediments, but deform as the sediments were moved up and down and compressed and faulted. And you can see these layers going all the way down until you get to the plate boundary. Now, we talked about the terrigenous sediment cycle, which is how you get the sediments into the ocean. And so this, again, is a cycle where we have uplift of continents, and then those mountains and the continents erode through chemical and physical weathering, and then are transported into the ocean and deposited on the ocean plate and form the sediments that we're going to be talking about today. Now, along the margin of continents, you have two different types of continental margins: active margins, and these occur where you have subduction of ocean plate occurring. So again, that's where we get these deep trenches, very steep slopes with little continental shelf. And so an example is most of the US West Coast and the west coast of South America. In contrast to where we have passive continental margins, this is where we have where we're nearby seafloor spreading. So for example, the US East Coast and the Atlantic, you have seafloor spreading in the Atlantic, but the ocean plate is welded to the continental plates. There's no subduction there. You get a gentle continental slope with a large shelf and a continental rise at the base of the slope. So much shallower angle overall, not as steep as in active margins. So looking at the east coast of the US, this is one of the passive margins. And here, so we've got this wide continental shelf, a gentle continental slope with a rise down below the slope going down to the abyssal plain. And if we look at a cross-section of the East Coast, so this is a cross-section here, we have the coast on the left, the coastal plain, and then sea level on the right. Sea level is this line here dividing the ocean from the atmosphere, and then we have continental rock and sediments above. And really we can see history going back to the break of Pangaea in this cross-section. So the oldest part, this deepest rock down here, shows faulting that is remnants of rift valleys. So about 200 to 145 million years ago, we had rift valleys forming in the Triassic, and you get these faulted blocks. This is where a new ocean formed as this spread apart. And then after that, in the marine sediments from the Jurassic, you get sediments and salt deposits as these ocean basins periodically dried out. Above those Jurassic marine sediments and salt intrusions, we have very thick continental and shelf sediments from the Cretaceous and Cenozoic, and these buried these salt deposits. And also we have examples of buried reef, where reef was growing up along the coast as this plate subsided. Eventually it could not keep up with the subsidence and was buried with sediments. These sediments end with the KT extinction event that we discussed earlier, about 65, 66 million years ago. And after that, this is where then the Cenozoic sediments lay on top of the Cretaceous sediments. And it's important to realize that these accumulation processes are ongoing today. So as we have erosion from mountains and sediment transport offshore. The mountains then are a bit lighter, they'll float up a bit more, while the shelf is weighted down and subsides a bit more. Another type of sediments that you can find are in shallow epiric seas. These are inland seas where you can have the sediments getting quite shallow. So Gulf of Mexico is now relatively deep. It used to be quite shallow. About 180 million years ago, there was periodic evaporation of the waters in this isolated basin, and you got really large salt deposits that would form on the sediments. As the Mississippi sediment plumes came out and pressed down, these salt deposits formed domes that rose up, and as they eventually broke through the sediment and were covered with and interacted with water, they would dissolve and leave behind these pockmarks. These pockmarks also accumulate hydrocarbons. So this is one of the reasons that the Gulf of Mexico is so rich in hydrocarbons, and why there is so much oil there to be extracted. So one of the things we can learn from sediments is how sea level has changed in the past. And so it's possible to understand these layers to essentially get this stratigraphy using different methods. So right now, people use air guns, which essentially create a lot of loud sound from burst of air. They used to use dynamite to create an explosion, but the same idea applies. You make a loud sound and it travels through the water and it reflects off different surfaces in the water. And so by knowing how sound travels in the water and through different sediments, you can develop these layers by recording the reflected sound in using a hydrophone. And so this can help us understand past sea level changes and understand sedimentation and formation rates of bottom sediments. So the way you do this is through sequence stratigraphy. So here we have a cross section of the Great Bahama Bank, and there are all these little sediment layers that you can see in these lines. And so using multiple cores drilled down, each of these lines represents a different drill site, you can try to establish uniform time periods between the layers measured. And the way you can do that is by using different types of correlation. So either lithostratigraphy, biostratigraphy, chronostratigraphy, or magnetostratigraphy. I'm not going to go into all the details here yet, but just to describe them a bit. So lithostratigraphy is the identification of physical boundaries to recognize changes in geologic conditions. So essentially seeing where these layers are and where they seem uniform, you can understand how different areas accumulate sediments at different rates. Biostratigraphy is using the organisms and the shells, not living organisms, but the remnants of organisms. So primarily the hard shells like calcium carbonate or siliceous shells to establish where uniform layers were. And this can be very helpful for timing because you'll know more or less when the sediments were deposited based on other independently dated times where these organisms lived and how abundant they were. Chronostratigraphy is based on the age of materials, so you can use radiometric dating to know how old the material is and use that to create these layers. Or magnetostratigraphy is when you use a sequence of magnetic reversals in the sediments and measure the patterns in your core, you can then date the sediment using some known record. And finally, you can also use stable isotopes. That's beyond what we're going to get into right now, but essentially isotopes are incorporated into shells in different ratios. So heavier and lighter isotopes of things like oxygen or carbon are incorporated into materials at rates that are often temperature dependent or can be impacted by other aspects of the environment. And so by knowing both the relationship between that fractionation, whether lighter or heavier isotopes are taken up, as well as the distribution of where your sediments are and what organisms are being captured in those sediments, you can understand the conditions in the past. And so what we see on this lower plot here is a power spectrum of sea level that dates back millions of years. So on the x-axis is frequency. So this is in cycles per million year. So if you had 2 cycles per million year, that means you've got a period of 500,000 years. So this is essentially understanding variability in sea level and whether that occurred on some sort of regular time period or not. If you had 8 cycles per million year, that's a period of about 125,000 years. The y-axis is what is called a power spectra. So that's essentially how much variability in sea level is happening at these different time periods. And so what comes out of this, what you can see is there are distinct peaks in the sea level variability. That means that sea level is not just randomly changing over the past several million years or tens of millions of years. It's changing in part according to these regular cycles. And this is largely related to the amount of solar insolation or the amount of sunlight that's hitting the Earth. So it's got, it's essentially cosmogenic forcing, I guess you could say. These astronomical periods are called Milankovitch cycles, based after the guy who figured out that there are these regular cycles, and they're due to changes in the tilt of the Earth's axis or distance from the sun that impact how much sunlight hits the Earth. And this is important because the amount of sunlight that hits the Earth, the amount of energy going to the Earth, in part determines how much ice is present on the Earth. And if you have a lot of water bound up in ice, then the sea level will be lower. So you essentially have movement of water between the ocean and land ice that in large part causes these long-term sea level changes. So what else determines sea level? So I talked about I was just talking about global causes, and we'll go to those again in a minute. But locally, you can have changes in water motion from storm surges or wind-driven waves along the shoreline. You can also have tectonic uplift or subsidence. All of those can impact sea level in a very local scale. Globally, you can have eustatic changes. So these are changes in the total volume of the ocean. It's an important term to know. And this can be due to the ice volume that's stored on continents. This can be due to changes in mean sea floor spreading rate. So fast spreading, you have a younger sea floor and sea level rises, whereas slow, older sea floor, the sea level will fall, or changes in mean ocean temperature. So if you heat water, you decrease the density and you increase sea level. And because this is happening, if you're talking about global changes, you can, a small change in density can make a big change in sea level. So one thing to consider, so if you just pause for a second and think about, would melting Arctic ice cause a change in sea level? And people often sort of can make the assumption that it would, that if you melt ice, you're adding to sea level rise. But that actually is not true. If you have sea ice, so most of the ice in the Arctic is sea ice, that's floating on the ocean already. So there's no change in ocean volume, whether that water is bound up in ice or in water. So that's similar to the isostatic equilibrium that we talked about earlier. Only land ice matters for sea level. So if you have ice, or if you have water bound up in glaciers or ice sheets, and that melts, that will impact your sea level rise. But just melting floating sea ice doesn't impact sea level rise. So that's an important distinction and something to keep in mind, especially as you read the news. So sea level rise over the last 18,000 years or so, sea level has been rising. Prior to that, sea level was falling. And so C on this plot is present day. This is height above or below present sea level in meters. So sea level used to be quite a bit lower and then was higher. And so what you're seeing here is the glacial interglacial cycle. So A here, this is the maximum of the last ice age. So a lot of water was bound up in land ice, in glaciers and ice sheets. Whereas B here was the last interglacial period. And this actually had smaller ice sheets than there were today. And sea level was about 6 meters higher than it currently is. The eustatic sea level change, so this is total based on total volume of water, has risen about 20 centimeters over the last century, largely due to melting of glacial ice. You also have had warming, although the current warming from global warming hasn't fully equilibrated with the ocean yet. So that there's sort of a time lag built in there. And then there's also a local effect of Hawaiian geology on relative sea level rises of our islands. Because as we discussed in the ocean hotspots lecture, the islands are subsiding as they move off the local hotspot. And so you have both sea level rise and the islands moving down. So you have a greater overall apparent sea level rise. So just to summarize, we talked about sediment classification. We in part by formation. We talked about active and passive continental margins. We went over stratigraphy and how that can be used to establish common depth levels in the sediment. And we talked some about sea level changes, both local and global causes, and how it has varied over the last couple 100,000 years.